Hello, Dr. Varun. Can you hear us?
Yeah, I can hear you. Hello.
Okay. Yes,
Yeah.
yes, we can hear you, sir.
Okay.
Okay, so I'll just so we have nine astrobiology and space science students over here who will be attending this talk. It's just a guest lecture on atmospheres of planetary bodies. Uh,
Good.
Yeah, so just give an insight to the students about Dr. Varun Sheel. He did his bachelor's and master's in physics and his PhD at Physical Research Lab, Ahmedabad. And he focuses mostly on the study of effect of space weather on Venus atmospheres, impact of dust on the Martian lower atmosphere, and also radio science experiments for Venus and Mars. And of course, Dr. Varun Sheel, if you'd like to add anything more to that with respect to some of your recent latest work, we'd be very happy to hear it. With that, I would like to give you the floor so that you can begin with the lecture, sir.
Okay. Thank you. So, shall I share my screen?
Yes, sir.
Okay. Share screen. Can you see the PPT?
Yes.
Make it in the full screen. Yeah. Is it visible now?
Yes, sir. It is.
Okay. Okay. So, good morning. Good afternoon to all of you. We are this morning in Germany. So, uh, thank you for inviting me for this talk, lecture on atmospheres of planetary bodies. I believe all of you are doing a master's course in astrobiology, and one of the most important aspects of space exploration is in astrobiology because it's our quest to find out whether we have life in other planets or other systems, and uh, mostly this comes under the domain of habitability. And this has become our the frontier research area. In fact, we recently had an international conference at TRL where we discussed planetary solar system and exoplanets, where we believe that there could be a possibility to find life, and in context of that, even habitability. So these are issues which are coupled to each other, and you must have gone through a lot of courses and will go through on various aspects of astrobiology. So here, what I will focus on is there are the atmospheres, which, as you can, I mean, all of you know that if you want to find life, atmosphere is the most important component. And wherever we have atmospheres, especially I will talk of the terrestrial planets, we are still trying to find out whether life is possible or not. So, with that, let me just begin. This is the uh, an overview I'm giving you here, that we have different planetary bodies. And if you look at the solar system planets, they can be divided into these four different types. And uh, the idea is that all of them have characteristic features depending on their composition, the composition of the body itself, and the atmospheres. So, if you look at for example, the Jovian planets, which are the Jupiter, Saturn, Uranus, and Neptune. So, they have basically a massive hydrogen-rich atmospheres, whereas terrestrial planets, which are sort of, we call them as rocky planets, the basically the Venus, Earth, and Mars, they have, the thick atmospheres as we know them on Earth. And if you go to the some of the moons and smaller bodies, some of them are icy, and they also might have some signatures of atmosphere. For example, comets. This is the atmosphere of comets has also been widely studied. We do that at PRL, and the other moons like Titan, Triton, and Pluto. So there are these other classes of bodies in the solar system which are called airless bodies. So they don't have atmospheres. Uh, for example, the Mercury, asteroids, and especially our moon. So the moon, as we know, does not have an atmosphere. But recently, from the studies of Chandrayaan missions, which India has recently launched, we have seen that very small amounts of uh, ionosphere have been found. I will come to that a bit later. But mostly, for your case, I mean, for the students, you can assume that they do not have atmospheres. So this is one of the pictures I'm showing you is basically showing you a different type of clouds. So these are three planets, and you can see that there are clouds on them, and there are different types of clouds. And the idea is that if you look at the Earth, for example, this is the satellite image, and these are covered by these water vapor clouds, and these are typical pictures which you see on and off from weather monitoring systems. Then here we see Mars. In fact, this is the picture taken by our own Mars color camera from the Mangalyaan mission. And if you see here that these are basically dust clouds. So that I will come to a bit later. Uh, and if you see Venus, again, you have clouds, but they are of a different nature. They are basically composed of sulfuric acid, and they are found at around 50 to 70 kilometers in the Venus atmosphere. And for Mars, as I said, dust is a very important issue, which I have worked on for many years. And dust lifts, there is a lot of dust in the surface. When it lifts up, it almost sometimes engulfs the entire planets. And these, you can call them the clouds of dust, which can be present there. So, three different planets having clouds of different type, but in terms of their physics and the science, they have similar properties, and that is what we are trying to study, that how they are different from each other and what we can learn from the other planets. Maybe Earth was at one time such kind of a planet. So if you look at the first thing we would like to know, the atmosphere, is a composition of basically gases that surrounds the surface of any planet. And this is sort of a comparison which shows you the kind of composition structural differences which you have. And if you look at the terrestrial planets, for example, Earth is dominated by nitrogen and oxygen, whereas if you see Venus and Mars, they are mainly CO2 dominated, 96% CO2. And that is what makes it quite different from Earth. And we'll see that a bit later. And of course, Mercury, we have a little bit of oxygen. But on the other side, if you see gas giants, they are mainly hydrogen dominated. So, in terms of the composition, also they are quite different, and that again affects the other properties as well. This is I'm just comparing the terrestrial planets, and if you see here, there's again the same. Whatever I told you that the CO2 is more dominant on Venus and Mars. But if you see the smaller amounts of gases, which you must be familiar with, they're called trace gases. For example, methane, you know that it is found in the Earth's atmosphere. It's an important constituent. It is also there on Mars, but we have still not found very convincing uh, signals for methane. There have been missions which have tried to observe it sporadically, but we still don't know what are the sources of methane, and we don't have any confirmation about its variability. Even India had a mission on Mangalyaan, which tried to observe methane, but this is still a debatable topic. It's still an open question in science. Water vapor, for example, water vapor is there on Mars and Venus as well. As I showed you, it plays a very important role in the Earth's atmosphere. It's a greenhouse gas, and that is a major lifeline of Earth. But it is present in very small quantities on Mars and Venus as well. And it does play an important role. I'll come to that a bit later. And then we have other minor species like argon, etc. So, apart from the major constituents which demarcate these planets, you have these minor constituents which, just like in the Earth's atmosphere, they play an important role, especially, for example, in Mars and Venus, because you know that in the Earth's atmosphere, I mean, we don't even talk of nitrogen and oxygen. We are today the buzzword is the climate change and global warming, which is mainly due to the smaller amounts of greenhouse gases, which are very less in number. So, but then these are the constituents which play a major role in the climate. So in terms of composition, we know mostly these planets, and we have a lot of observations. Now, the other second important characteristic of an atmosphere is its physical structure. So, when you say an atmosphere, we can differentiate this planet or the atmosphere is depending on the kind of physical structure it has. And when I say physical structure, then we're talking of pressures, densities, and temperatures. These three quantities, these physical quantities, define the structure of an atmosphere. And this is exactly what now even we are searching for in exoplanets, which are beyond the solar system. We have discovered many of these exoplanets, and two of them have been discovered by PRL through our telescope, which we have at Mount Abu. Basically, any planet we are searching for, if it has an atmosphere, we would first like to find out its pressure structure, density, and temperature structure. Now, this is some of you maybe who are from physics background will appreciate this. This even for physical chemistry, chemical background. So this is the ideal gas law, which many of you are familiar with, and this relates basically the pressure and temperature. So two of the parameters which characterize the atmosphere are already related here, and this is a law which we take into account in many aspects of our studies in the atmosphere. And there is a very simple derivation, which again many of you might be familiar. That's called the hydrostatic equation, and that assumes that if you take a column of air, it is, and you consider that it is in equilibrium, then that results from the fact that the pressure gradient forces which are acting on this column of air is balanced by the gravitational forces, because these are the two forces acting on this parcel of air. So this is basically the pressure gradient force. This is the gravitational force, and if you balance them, you can basically arrive at this kind of an expression, which is called the hydrostatic equation. And this is something which all of you are very familiar in basically fluid mechanics or physics, or this is valid for any kind of fluid. So you are basically treating air as a fluid. And the result of this hydrostatic equation is that if you integrate this equation, then this basically leaves you to the following expression. And this is basically tells you that how the pressure varies with height. So dz is the height. And while integrating this equation, you look at the equation which we had earlier here. If you integrate this equation, then there is a term here which comes which is basically kt by mg. And so you are this is basically, if you see, it has a dimension of length, and therefore this is called a scale height. This is if you look at this h, this is a scale height where the pressure is the height at which the pressure decreases by 1 by e. So this kind of a variation of pressure, and similarly the density from ideal gas law will follow a sort of variation similar to that of pressure. So we were talking of the physical structure of the atmosphere, which is characterized by pressure, density, and temperature. So you see here already that pressure and density variations, we understand it the way it's written here. It's basically exponentially decreasing with height. And in that process, we arrive at something called a scale height, which is characteristic of the atmosphere. And this is, you can see here, I've shown you for the 3 different terrestrial planets, how it varies. And you can see here that, for example, this is the scale height for Venus. It is quite high, 16 kilometers. For Earth, it is 8.5 kilometers. And Mars is similar to that of Venus. And this is because you have the expression of temperature and mean molecular mass of air coming into the picture, and that is how. And the gravitational constant is different in the different planets. So here, the temperature, the g, gravitational acceleration, and the mean mass of air molecule, that determines the scale height. So basically, this is again a characteristic of the atmosphere. So these are the 3 kind of moment, we recognize each other by our name. So this is the kind of thing which you recognize in atmosphere by. If you tell it scale height, you say, oh, okay, this is Venus, or this is Earth's atmosphere, this is Mars. And this is again a similar thing you do for exoplanets. We cannot, it's very far off, so we cannot really observe its atmosphere through missions. Space planetary exploration missions, but there are techniques to construct temperature profiles of that planet, and that is how we characterize that. Okay, this is what the physical structure is. So then next we come to the temperature, which is the most important characteristic of a planet. And you see here there is a very simple formula that if the planet is in radiative equilibrium with the radiation coming from the sun, then if you treat the planet as a black body, it absorbs the radiation and radiates back. So, for example, the Earth radiates back in the infrared. And from a simple formula, you can show that it's by equating the radiance from the Planck's law, one can actually derive the average temperature of the planet. That is the temperature at the surface. And that is what the temperature is given to the near surface atmosphere. And if we work this out, we find that the temperature of the Earth or any of the planets will be slightly lower than what is actually observed. And all of you know that this is a phenomenon called the greenhouse effect, that if we do not have an atmosphere, the temperature is much less than what we would experience with an atmosphere. So the atmosphere is creating that greenhouse effect, trapping the radiation, infrared radiation coming from the planet. And that is what gives you the higher temperature, livable temperature, for example, in Earth. But this greenhouse effect is there in other planets as well. So the temperature structure, actual temperature structure, depends on the composition of the gases. And so that is the mean surface kind of a temperature. But again, as I said, the actual characteristic of the atmosphere comes from its vertical temperature structure. And if you look at this figure here, it shows you two kind of the structure of three planets, the terrestrial planets, and you notice that how different they are. For example, the Earth has a very definitive structure in terms of the temperature, and this will I'll show you again later. And all of you know that the temperature decreases initially. That is the normal trend because the source of the heat infrared is coming from the radiation of the radiative effect of the planet. And it decreases with height, so that is natural because the source is the surface of the planet. But then on Earth, as you know, there is a stratospheric ozone layer here, due to which the temperature increases because of the absorption of UV radiation. But that is this amount of ozone is not present in the Earth's planets. Mars, some amount of ozone is there, which I'll come to it later, but not enough to form a particular layer called just like we have in the stratosphere of Earth. So such increase in temperature you don't see in the other planets. And then of course the once the ozone layer is over in the Earth, the stratosphere, the temperature decrease continues. It is a normal trend. And then when the densities are very less in the upper regions of the atmosphere, it increases because there is less of collisions to create that temperature. So this kind of a temperature structure is something which we have understood over the years of different planets through missions, through theory. And this is a kind of temperature structure which we also construct for say exoplanets. So beyond our reach of the solar system, we cannot send missions there, but through some spectroscopic measurements, we can construct a temperature profile. So, and that is how we recognize that planet. So what I've shown you is that the physical characteristic, the pressure, density, and temperature are the recognition of a planet and how they vary from each other. And this typical vertical structure, this is the result of various radiative processes, which I will come to next. And that is what determines this vertical structure, because what I've shown you here that it is the solar radiation which is interacting with the atmosphere. And once that happens, there could be different kind of processes. For example, you could knock off an electron and create an ion. Simple molecule, just knock off an electron, and what remains is ion. And those ions, when they are present, that's called an ionosphere. You could also dissociate a molecule with the photon energy which is coming. So that is called photodissociation. And also, what could happen is that mostly this is a phenomenon which you ever observe in the visible region in Earth. There could be scattering and absorption. So typically, you know, the sky is blue because of scattering, and absorption happens, for example, in the infrared, we're absorbing the heat and all that. So once the photon, the radiation is there, all these processes occur. And it is a combination of these processes because there are different species in the atmosphere. So depending on which species absorbs which wavelength of radiation, the total radiative budget of the atmosphere can be determined, and that is what leads to the temperature structure which we saw. And this domain of science in terms of critically understanding it is called the radiative transfer. And we also have various observations which make use of these kind of processes. So if we look at this kind of temperature structure, I had already shown you for the three planets in general, comparing them. But all of you are very familiar that this is the temperature structure which defines the different layers of the Earth's atmosphere. So in the lower layer where the temperature decreases with height, it's called the troposphere. And this is the stratosphere where we have a lot of ozone and overheating due to the UV light occurs. And then upper in the upper regions, we have the thermosphere where the temperature increases because the density is very less. And you also have formation of these ions. I have told you that the photons can knock off an electron and ionize the species. So we'll come to that a bit later. But basically, these layers, which you know, the names of the layers for the Earth's atmosphere, they are based on the temperature structure. And similar names you can give for other planets. So for Mars and Venus, you have the troposphere, but you don't have a stratosphere. And then you have the thermosphere, and upper region around 200 kilometers above, you have the exosphere. And then there is this typical thermodynamics. If you are from physics background, you can apply the first law of thermodynamics, and that will give you an expression called the lapse rate, that how far the temperature is varying. This is again comes from the physics of the atmosphere, how the solar radiation is interacting with the atmosphere in different molecules, the absorption, scattering, and all that will give you a sort of a decrease of the temperature with height, which is called the lapse rate. That again is different from different in different planets because it depends on the gravitational acceleration and the specific heat capacity, uh, depending on the composition. So you typically see if the Earth's atmosphere is 10 degrees per kilometer in the troposphere. So this is for the troposphere, and it's quite different from Mars. Venus is also almost similar. So this kind of what picture I've given you, there are a lot of physics in this atmosphere where the solar radiation is interacting with the atmosphere, and you have radiative effects, which gives rise to temperature structures and the pressure variations are anyway there. And all these coupled to each other, they give rise to different physical processes in the atmosphere. And just to show you that different layers are there in the Earth's atmosphere, which all of you are familiar, but they are mainly classified into based on the temperature structure. Now, the point is that we have this information about the atmosphere, but how do we get them? How do we study these different processes, and what do we get from that? So, as obvious, the first way to study anything is through observations. And this is just a simple idea I'm giving you, but there are a lot of details into it. Most of the parameters which you measure in an atmosphere, whether it be the physical structure, temperature, pressure, or nowadays we are measuring even the trace amount of gases, they are based on the backscattered radiation from the atmosphere. So, as I said, that the radiation interacts with the atmosphere, many wavelengths, the whole solar spectrum is coming, and the kind of interaction varies with different wavelengths. And depending on that, some radiation is coming out of the atmosphere. So, basically, the satellite is just observing that radiation. And from that observation of the radiation, you derive different quantities. And that is called the process of retrieval. So this is what I've shown you in a very schematic way, that what you observe is only the intensity of a radiation at a particular wavelength. And then you sort of have a model to say that, okay, if this was the case, what would have been my radiation reaching the satellite? And then fine tune those parameters and arrive. For example, typically I'm showing you for say the ozone composition. For our Earth now it's like it's a peanut kind of a thing that every day the satellites are observing how much ozone is there. Like they're observing clouds, and so this thing are very well advanced. So when you measure ozone, you're just telling the amount of ozone there. And that happens because ozone absorbs the UV radiation. So that much amount of UV when the satellite observes in the UV range, there will be a absorption gap there. And that is what you then try to model, that if this much ozone is there in the atmosphere, how much absorption in the UV would have been there. But this is what you observe. So you fine tune the ozone density to your match the theoretical predicted intensity and the observed intensity. And then you say, okay, this is my amount of ozone in the atmosphere. So as I said, for Earth now, it's a routine thing. We are measuring very small amounts of gases, CO2, ozone, methane, everything is continuously being monitored. All these measurements are based on the same technique. For other planets, we have done it for Mars, Venus. I will come to ozone slightly later. We have mapped the entire planet. We know how much ozone is there. They are very small amount, but now the technology and science and physics and mathematics is so advanced that we can detect them. And this is the principle. Not only that, temperature, pressure, everything is detected from here only. So the observations are remote sensing observations. And that helps us to discover these atmospheres. The other very important, one of the important experiments is called the radio occultation experiment. And the principle of this experiment is that when a satellite is moving around a planet, say Mars or Venus, we are sending these missions. So just before, because where this is the Earth station which monitors the satellite, is receiving the signals from the satellite. And when satellite is about to go behind the planet and get occulted by the Earth's line of path, so that the signal is not reach here. Just before that, when it sends those radio signals, these radio signals experience a slight bending in the atmosphere due to the change in its refractive index. And that is used to construct the entire temperature, pressure, and density profile of the atmosphere. And this is a remote sensing experiment from where there is a transmitter which sends out the radio waves, and we're just recording the radio waves at the ground station here. And because of the small bending in this radio signals, there is a small Doppler shift observed in the frequency of this radio waves. And with that, I will show you how you retrieve. So, but this is a basic, very accurate experiment to measure the vertical pressure, temperature, and density profiles. And this is an experiment which we have proposed for the future Venus and Mars missions going from India. And that was what brought me to Germany, because we are collaborating with one of the experts in the radio occultation experiment was flown this on other missions like Mars and Venus from Europe, from the European Space Agency. And we are a collaborative project where we're designing our instrument to measure this atmosphere there in Venus atmosphere. So probably Venus will be the first mission which will go from India in a few years from now, and later Mars. So this is a radio science experiment which basically measures the profiles of the atmosphere, which I just showed you earlier, pressure, temperature. And this is a kind of retrieval. Here the retrieval is slightly different in the sense that I told you most many parameters in the observations are intensity based, and they measure intensity of different wavelengths and then infer some quantity of the atmosphere. Here, what you are observing is just pure Doppler shift in the frequency. So these are typically the X band frequencies, say in 8 gigahertz, and or the X band frequencies. And these frequencies are the same which are used to track the satellite and download the data. And these frequencies, they undergo very small Doppler shifts of the order of millihertz. And that is what we have to detect. And then once we know this, so this frequency is recorded at the ground. And once we know the geometry of the spacecraft, which comes from the mission data, And then we do a lot of mathematics here and calculate finally the refractive index, which then can lead into the different parameters in the atmosphere like the pressure, temperature, and density, and also the electron density. So electron density is a representation of the ionosphere. So as I told you that the radiation, if they are strong enough, they can ionize the neutral species, and then what you're left with are ions and the electrons. And you can basically measure the electrons densities from here, and that characterizes the ionosphere. And many of you might be aware that the ionosphere is a part of the atmosphere, like for the Earth's case, where certain transmissions are done, and it acts also as a source of charging of the region there and producing electric fields, maintaining the electric fields of the Earth's atmosphere. I'll come to that a bit. So this is how we observe the atmosphere uh, in different parameters. And that is how we have got now very good knowledge of the atmospheres of Earth, Mars, and Venus through different missions. Then the next is that the other aspect of any science is you theoretically understand the concept. And so then the question is that how do we theoretically understand the atmosphere? And that is nothing but modeling the atmospheres. Now, here the challenge comes from the fact that the processes which are occurring in any atmosphere, they occur simultaneously and they are coupled to each other at different scales. So, what I'm showing you here are the processes in any atmosphere. They can be divided into these three classes. If you take anything, for example, if you take the Earth's atmosphere, which you are familiar with, there is a lot of motion in the atmosphere, which we call as winds. And those are called dynamical processes. So, and there are different scales. You could have small regional scale breeze. You have the large scale monsoons over thousands of kilometers, and there are motions which go from southern hemisphere to northern hemisphere. So this kind of a dynamical processes are taken into account through equations. So those are that's called the dynamical process, and then you have physical processes you could call them like precipitation or heating of the atmosphere or some other kind of so these processes. And then of course the atmosphere is a composition of gases, so you have a lot of chemical reactions and chemical processes going on. And then this I've already talked about that the solar radiation is the main source of energy, and when the solar radiation comes in different wavelengths, you could have scattering, absorption, and photodissociation, ionization, which I talked about. All these are called radiative processes. So basically, the point here is that they are all coupled to each other. They're not occurring isolated because it's a real system. The chemical species are interacting with each other. Ozone is being produced, for example. Ozone then absorbs the ultraviolet radiation, and that causes a temperature change. And ozone is being redistributed amongst various parts of the atmosphere through dynamical processes. So all these processes are coupled to each other. And therefore, this calls the need to solve them numerically. So the processes themselves are maybe relatively simple, but there are too many of them occurring at the same time. And if you want to realistically understand the atmosphere, you have to take into account many of them at the same time. And that is how our models have developed over the past few years. And again, giving analogy to Earth atmosphere because you are familiar, that is how today the way we understand our climate, the climate models, the way they are predicting is very different from what we understood it 3 decades back because we were more start of these processes. We were doing some simulations, we were chemical, but when we combine all of them together, the models became more and more complex. And today we have full climate models, which we take into account different aspects of our atmosphere and their effect on different parts of the atmosphere, which is very important. So, critically understanding the atmospheres is challenging in the aspect that you have all these processes occurring simultaneously. So, we take recourse to numerical techniques and solve them. So, just to give a small glimpse of how we model the three types of processes which are shown in here. So, first we come to the chemical lab. I've already shown you different types of compositions the planets have. And since there are different species, you will have reactions to a species reacting with each other and producing, say, one species or two other species. So, in general, you can write a reaction in this way. And here we want to find how fast this concentration of C is changing for a number of species C. This is how we model that. It's basically depends on A and B and the rate constant of this reaction. This rate constant basically measured in the laboratory. So this will give us how fast the species is being produced or how fast this bracket the concentration of C is changing. So a bit of chemical chemistry here. Some of you are familiar. And in general, so this is for even if you want to find the change of species D, can be written, it depends on this same similar A into A to B. So in general, suppose you have various species, about 10 to 15 species you want to consider for a small region of the atmosphere. This is the general equation you can write on based on this. And this tells you the variation in the density of a species I with time. It depends on the productions of the species from different sources and the losses. So this is the kind of a differential equation where I is one species. So I can be running from, say, you could have 50 or 100 species you can consider in a model depending if it's again the Earth's atmosphere, you would have more complex species, more pollutants. And so this would be a sort of a chemical model. You're modeling the chemical processes, and we would have one differential equation for one species for the production loss. So like that, if you have 50 species, 50 differential equations, all of them are coupled to each other and you numerically solve them. So chemically, we are producing a system in equilibrium where all the species are contributing to each other. Then a small example I'm giving you that is of ozone. Again, we know that very well for the Earth's atmosphere. This is how you produce ozone. This is the only way where you Earth is dominated by oxygen. So it is photo-dissociated in this wavelength, so the solar energy. And once you have oxygen atom produced from oxygen molecule, this reacts with the other oxygen molecule, the free body, and produces. So only way to produce ozone in any atmosphere is this. And after production, ozone is also getting lost through three different channels. So you are producing ozone and it is getting lost. So then after certain time, an equilibrium is reached. And each of the reactions has different rates at which it is happening. So whatever I showed you earlier, the theoretical equation, you can write down a current because here you have, if you see three species, O2 molecule, oxygen atom, and O3 molecule, ozone. So this is the oxygen gas molecule, oxygen ozone molecule, and the oxygen atom, O, O2, and O3. So these three species, you can write down the differential equations. And this is O1, O2, O3. And there you have the production of each of the species and loss. The production is with the positive term and losses with the negative. So typically you are solving these three differential equations simultaneously and you get an equilibrium concentration for these three species. That is what your model constitutes of. Now, but when as I told you that all these processes are coupled to each other, so we are modeling the chemical part of it. But as you know, the motion of the atmosphere is very important, and that constitutes the dynamical part of the dynamical processes. And a simple way to model that is to include a term of the the motion of the wind or the air parcel, which is basically called the wind, into the equation. So now earlier you had the density varying with time and only production and loss. Now you are including a gradient of the velocity of the wind. V is the velocity of the wind. So this is now a partial differential equation. And what you have done is that you have included the motion of the air as a wind component. So this is the velocity, wind velocity. And you see here, this is nothing but a moment. This is a mass continuity equation. And if you derive it from simple physics, it basically represents the conservation of mass. And this you can solve using appropriate conditions, equation, initial and boundary conditions, and that will give you the distribution, the density of any species varying with time and space in the atmosphere. And that will do. People are really interested in how any species is changing. For example, trace gases, greenhouse gases, how they're changing with space and time in the atmosphere. And if we make them, this is these kind of models are called chemical transport because you have chemistry and you are transporting the various parts of the atmosphere. But there are lots of models which are called the general circulation models, which I come to slightly later, which basically solve even the motion part of it. So you are prescribing, you have to input certain velocities of the winds, which is causing the motion. But if you simulate these ones, then it's called a general circulation. So now the third part of processes I described, the other radiative process. And there I told you that when the solar radiation interacts with gaseous molecules of the atmosphere, you could, for example, have photodissociation. So this is a typical example of a photodissociation. The ozone, I showed you even in the ozone chemistry, this is why ozone is lost. It is broken up, called dissociation by the protons. So photodissociation breaks up into oxygen atom and molecule. And you want to calculate how fast this thing is happening. So if you take a general form of such reactions, X proportional to some other species, then the concentration of the species varies proportional to the original concentration of the species here. And J is the rate constant. So this is something which you can actually calculate. Like for other chemical species, these rate constants are basically measured in the laboratory. Where the photodissociation rate constant, you can calculate because that depends on the flux of the radiation coming in from the solar, from the sun, and the absorption cross section of these molecules. This is again measured from the laboratory. So this is the kind of theoretical expression you can calculate. But the point is that this solar radiation, it also interacts with this particle through absorption and scattering. So we consider, say, for example, at 100 kilometers, the radiation is not attenuated at all. There is no absorption scattering. After that, your species in the atmosphere, nitrogen, oxygen, or carbon dioxide in Mars and Venus, they start absorbing and scattering the radiation. So the intensity starts attenuating. And this is a kind of radiative transfer equation you would use to calculate such kind of an attenuation. From simple laws, which be a Lambert law, scientists gave, they said that if the intensity absorbs or scatters in a small path of the medium, then that depends on the optical depth of that medium, which involves the density of that medium, that is the atmosphere, and an absorption or scattering cross section, which you can measure or define. So when you use the species, this kind of a radiative transfer equation, you can basically calculate how the intensity is varying from at different heights. And that is what radiative transfer calculations, modeling theory does. It calculates different amount of radiation reaching the surface. This is important, for example, in the case of Mars, where you would like to study what kind of is there a chance to find some species at the surface or life at the surface? Now that depends. There is a lot of UV radiation coming into Mars because it does not have a very strong magnetic field. So, and the atmosphere is very thin. So, a lot of UV comes to the surface. So, you can do calculations from here and see what how strong the UV is at the surface. And what scientists have found that a lot of UV reaches the surface. Even through observations, we have found that. So there is less likelihood that life as we know today on Earth will survive given the UV flux that reaches Martian surface. Whereas on Earth, that we are protected from this UV flux due to the ozone layer. So this is what I was referring to earlier, that when you have a chemical transport model, you prescribe the winds from outside. But here the general circulation models can solve the winds for you. And this is the kind of equations they use to solve. And you see here that again, this is the momentum equation, basically, which takes into account the pressure gradients, which create the winds. And it can give you the winds fields. So the GCMs can simulate the winds for you at different heights, at different latitudes, longitudes of a planet. And this is a theoretical prediction of the winds. Like every day you hear on the Met forecast that what the winds and temperature will be. The models here will simulate these things for you. It will give you the temperature, the winds, what it will be today, tomorrow, at different parts of the globe, at different heights. So these are the general circulation models, which took a few decades to develop over the last few decades. And today, in the last 2 decades, we have also developed them for other planets like Mars and Venus. So we are having climate models for Mars and Venus, just like we have for Earth. And this is the typical resources which are required to run such climate models. And we have, for example, a 1,000 teraflop high performing cluster at PRL, where we are running these climate models for Mars and Venus. So with this kind of background, how do we study the models theoretically? What are the science that we are trying to study in this through these methods in terms of the atmosphere? So the first important aspect I'll come to you, which was alluded to, that I've studied lots of uh, physics and science related to dust in the Martian atmosphere and what effect they have in its atmosphere. So this is just a schematic I've shown you here that what are the type of processing if you look at Mars, what are the type of processes occurring. So as I said that Mars lacks an intrinsic magnetic field. So what happens because of that, the particles from the sun, they directly come and enter into the Martian atmosphere. And therefore they will ionize the region much more than what is observed in the Earth's atmosphere. There will be a lot of ions present here. And that is a aspect we have tried to understand theoretically as well as through observations. We have made a lot of models here. I will come to that. And then we would have various components of the solar flux in terms of X-rays and UV. And at times we have these events, these huge energetic particles come, coronal mass ejections, which we had a week back all over the Earth, which cause a lot of auroras. So these phenomena can interact with the Martian atmosphere. And as I said, many of these particles can come down up to the surface. And here in the origin, what happens is that we have this dust here, which can lift into the atmosphere. And that can change the thermal structure of the Mars in a way which we don't see in the Earth's atmosphere. And I will come to that a bit slightly, later. And then, of course, you have the chemical processes as I talked about, the photochemistry going on, which couples to all these processes, and that is what we're trying to understand even on Mars, with small species like methane and ozone, how do they affect the climate of Mars. So basically, the Martian atmosphere, the climate is somewhat similar because you have seasons, and that comes similar to Earth, because that comes from the fact that you have a inclination which is similar to that of the Earth, and therefore the even the rotation period is slightly similar, but the length of revolution around the sun is longer. So you have almost 687 Earth days which this takes to evolve. But this the range revolves around here. That leads to different seasons on Mars, which is depicted here. And you characterize this through LS, which is the this angle which it makes to the sun. So the line here, uh, the angle which it makes to the star, this is equal to zero. We say that this is the spring, and then from here, whatever angle it makes, we go through uh, winter, late autumn, and then summer. So these are typical seasons which define Mars because of its revolution around the sun and its tilt, uh, axis of tilt. And this is the reason why you have this global dust storms on Mars. So you see that in typically the southern summer, where the southern hemisphere is nearer to the sun. Okay, here you have a lot of heating happening here because it's very close to the sun, and this is the southern hemisphere which gets heated up. And that is the time, where a lot of differential heating takes place, and the dust which was at the surface gets lifted up. And you can see here as an image which is observed from satellites. This is basically measuring the optical depth. And if you see here, that is uh, the red line, the red that shows you high optical depth. It means there is a lot of dust there. So if you see here, much dust was lifted in the atmosphere. But if you go through about later than June, you can start seeing small dust storms. So more dust means dust is lifting in dust storms. So this entire southern part of Mars is covered by dust. And gradually, by a few months later, the entire planet gets covered by dust, and these are called global dust storms. So this is a phenomenon which is very unique in the solar system. We have dust storms on the Earth as well, but here on Mars sometimes it almost every 3 years we believe, and we studied that it covers the entire globe. The whole Mars is covered by dust storms, and that is what a lot of scientists and myself in the past few years we tried to uh, do a lot of research through observations and modeling that how this happens, why, what are the phenomena involved. And there have been various missions which measure this dust. Again, is something which is measured remotely. So something called optical depth. Again, the intensity is measured that how much dust is absorbing. And normally it is measured at 9 micron. So at 9 micron, what is the absorption? That gives you the optical depth. So this dust storms means a lot of dust is there loaded in the atmosphere. And then this dust absorbs the solar radiation. And that can affect the thermal structure of the atmosphere there. It can cool down, it can heat, depending on the altitude of the dust. But also it affects the ionosphere. And ionosphere is a region I have showed you here schematically. As I said, solar radiation, they can knock off an electron and create ions. And these free electrons which have been created from a typical structure here, which is called the electron density. This is the electron density variation with height. And this is how these layers look like. For example, in the Martian atmosphere, you have these typical layers. Here you have the strongest ionization due to the extreme ultraviolet radiation. And then there are the layers down below, which could be due to the impact of these small meteorites which enter into the planets. They burn there and create metallic ions. And many of these things are again related to astrobiology because you could have this is one of the most outstanding questions that where did the water come from? Was it exogenic or endogenic? If it is exogenic, then it came through meteorites. And many of these meteorites which enter into these planets like Mars, Venus, and even Earth's atmosphere, and they burn, they leave behind these metallic ions here, which we can observe or model and try to study what is the composition and what we can find out from them about the possibility of life. So this kind of a typical structure which we know today through observations and modeling is the structure of the atmosphere. But we have developed a PRL, a very complex model which takes into account different ionic species here, solve the differential equations. And this is the kind of chemistry we consider for these ions. So we have the neutral atmosphere first. These are again the minor species which are found on Mars. Lot of chemical species, but very small in amount. Major is of course CO2. And when the photon interacts with each of them, they can first produce positive ions, just no carbon electrons. And then a complex chemistry is there which we have modeled. And we have found that hydrated ions are the most dominant ions which are produced in the atmosphere of Mars. Now, these hydrated ions, which what we have seen is that if we include the interaction of dust, so this dust aerosols basically gets charged, and these ions can attach themselves to these charged particles, and then the ions are destroyed. So this ionosphere, which we modeled, there are a lot of ions here. This ionosphere can be completely vanished during very large dust storms. That is one interesting discovery we have made. And this is open to the observations when we have certain missions which will observe these ions and by their densities, we'll be able to confirm that the storms have this effect. So this is one of the interesting phenomena which we have observed, that how dust impacts the atmosphere of Mars. The other thing which happens is the immediate near surface of Mars. Lot of turbulence is going on there. So these dust levels, these are convective vortices. I'll come to that a bit later. And they can lift a lot of dust, just like we have hurricanes on Earth. So they lift dust into the atmosphere and spread it all over. So the research emphasizes how to model this. Very difficult to know. So these are very dynamical structures. And this is very important from the concept of lander missions. India is proposing now next 4 to 5 years that we should go and land on the Mars, and maybe have a lander or even rover, because many of these rover missions have tried to find out some traces of life in some way, for example, methane, some animal species, or even the organic compounds to be have there, which will indicate that life is there. So if we have to have such sophisticated missions, we should know how these storms and dust levels can affect such kind of missions. And that's what we are doing at PRL. We have a weather research forecasting model, which is similar to that which we use for Earth. We are trying to predict, how this weather phenomena and dust levels can affect our missions. The other science in Mars, which very interesting, which was studied, and even now I could build that, is that of ozone. Now we know on Earth the ozone is about a few hundred option, 200 option. And this is the kind of conversion that we have. So like a column ozone. So at one place, if you construct a column, the entire column here, if you put one option, it means there's so many molecules of ozone per centimeter. And as I said, for Earth, it's typically around 300 oxygen at different places on Earth. But but this changes from place to place. And now it seems well that on Earth we have discovered the Antarctic ozone hole here where the ozone decreases drastically. And this was a phenomenon which was very dramatic, and it had a lot of political concerns, and it was solved by scientists. Where the ozone from 300 option unit, it can go up to almost about 50 option unit. So this is what happens on the Earth's case. Now, for Mars, as I said, very less ozone is there. We are talking of 300 options on average ozone column on Earth's atmosphere. Here it is hardly 3 options in it, even 100 factor less. But from satellite missions, we have been able to map the entire planet with ozone amounts. So we know this is the ozone column at different latitudes and longitudes on Mars. The entire map has been obtained, and this was part of my PhD student's thesis. Through observations, we did that, and we also then did it through a general circulation climate model of Mars, which had chemistry, photochemistry in that. And we saw that this ozone, the distribution of ozone is more in the higher latitude region, and that is because it is coupled to the water vapor cycle. So water vapor is a species which photodissociates and then it releases OS radicals. And OS radicals can destroy other one of the major loss process for ozone. So the higher water vapor you have, the more OS radicals, and it is a loss of ozone. So therefore, we have an active correlation of ozone and water vapor. And again, these species are very important in terms of life. If you have ozone, uh, as you know, that it can absorb UV radiation. So, though ozone is less on Mars, but this variation we are trying to study, and we have also proposed for future lander missions that we should measure ozone. So we have some indication of what kind of life we can expect on Mars. And again, the water vapor is there, but in very small quantities. But it is there. It is the main reservoir at the bottom where the polar caps on in the Mars, which release this water vapor from time to time. The third very interesting aspect of Martian science are these dust devils, which I talked just a few minutes back. And this is a phenomenon which happens when there is a differential heating at the surface. And because of that, the air rushes in, and then you have a convective motion, as I said, just like hurricanes and tornadoes you observe in the eastern United States. And such kind of whirlwinds, if they're strong enough, they can lift dust. And that it becomes visible. That is called, they are called dust devils. This is something, these are actual images taken from rovers based on Mars, which have observed these dust devils here. And again, the point of this is, again, we see we have analogs of this on in Ladakh. So Amity had a program last year that they were going to Ladakh because Ladakh is the site which is a good analog for the Martian surface. And there, there is question whether how this pressure drops, whether pressure differences can create such kind of convective vortices that can explain this dust devils. So, how do we detect these dust devils from a rover? The rover is continuously measuring pressure. And if you have sudden drops in pressure, even up to a few 3 pascals or even 2 to 3 pascals, that indicates that the convective vortex must have passed by. And this kind of observations have been done through a rover called Curiosity on Mars, and simultaneously it is measuring UV. So if there was a dust level, there would have been a drop in UV because the dust absorbs the UV radiations. So combined with these two observations, we could identify almost about 93 dust levels in the Martian atmosphere over for a year. So these phenomena, as I said, are very interesting because we are not able to predict them right now. We are having challenges in that. So scientists who are background of physics, maths, chemistry, and then we're trying to model and see if we can predict them so that for future lander missions, it would be very useful to study an environment whether we can really find life there. And theoretically also we can, in a simple, we can model these dust levels, but coupling them with climate model becomes very difficult. This is again, we have done a very small, simple calculation and we made a small model where we can predict the dust, how high it will lift up into the atmosphere, and what will be the distribution of this dust in the atmosphere. Again, these models, they have a very they are very coarse models, so we go down to very high resolutions where we can predict many of these convective vortices which are occurring in the atmosphere. So the other interesting planet is I've talked a lot about Mars because I've done a lot of work on that. The other interesting planet is Venus. This is a typical schematic of the atmosphere of Venus, which I've shown you here. And the Venus atmosphere has a lot of phenomena which we have still not understood, and that majorly comes from the fact that we have this cloud layer here, which prevents us from seeing the surface. And it's only the radars in a certain frequency which can go through this and see the surface. But otherwise, the thick cloud layer is something which we're trying to understand. And recent discoveries have shown that they could use phosphine where sort of being debated whether that could be an indication of life. So this region is very interesting, whether there is something we can find where some kind of, small uh, species or bacterial species can survive there. These are questions which are still very challenging. And to understand this, a lot of modeling is being done. In terms of observations, we had Venus, the, the European Space Mission, which launched the Venus mission. But after that, there has not been much. There's recently a Katsuki Japanese mission which is trying to observe various aspects of this atmosphere. But India has not planned, so I think within next the mission is getting approval in certain steps, and maybe in another few years, 2 4 years, we should be able to go to the payloads are already been selected, and many of them will observe certain aspects of this interesting atmosphere. Where the atmosphere, as you know, is rotating very fast compared to the planet itself. So that is called super rotation, and that leads to many interesting aspects. And that is again coupled to what is the possibility of finding life there. So this is just a glimpse of what science we can do. And just to end it, there is, I mean, just because we are familiar with Earth's atmosphere, so given the kind of, processes which we try to study, the pollutants, how it enters into the upper regions and then is coupled to the global warming, the temperature, the ocean, the dynamics, and all that is occurring. And we can also find out the effect of biomass burning on different atmospheric species in different regions, for example, Indonesia. So we have also studied the pollution in the Earth's atmosphere based on aircraft observations. So basically, what I've tried to tell you is that how the atmospheres for terrestrial planets, how they're different in certain ways, and how do we observe them, how do we model them, modeling has been one of my expertise. And then based on this, we are now planning for further exploration of these planets. We're building instruments. That is one of the major part of our institute. Right? We are with my department, Planetary Science Division. We are making various instruments which will measure various aspects of these planets. And of course, modeling is my own expertise. We're doing a lot of climate modeling of these planets. And the whole idea is that how once we are, of course, understanding today's atmosphere, but that will give us a clue how these planets are really, atmospheres are really evolved. That is again the question of what would have been there as in a form of life, or what can still be there right now in terms of the life that we don't recognize, and whether we should measure organics there. This is one of the major questions now. Even our next further moon missions that we will have are focused on volatiles and organics, because these two are the species which can tell us more about life. So we would like to know how water is there in the permanently shadowed regions of the moon. and how that thing came about and how are the volatiles there and organics, whether they are present or not, from different meteorites to study. But these things have their own signature in the atmosphere. For example, as I said, on Mars surface, whether life can exist, you have to first study the atmosphere itself, whether it has a conducive environment. Even if there is small UV, then we have forms of life which can survive in UV. So all these aspects are related to astrobiology, some aspects of the other, and understanding atmosphere is very important of that as well. And that's with that, I would like to end the presentation. Thank you very much.
All right. Thank you so much for that enlightening talk, sir. I'm sure the students really appreciated it. So just to give you an insight, we have a few students interested in physics and also a student who's interested in working in the atmospheric characteristics of exoplanets. And a lot of them actually come from a bio background. But since we are doing planetary meteorology this semester, I think some of the things that you had discussed, we've also discussed in class, like Stephen Boltzmann's constant laws and calculation and so on. So to the students, of course, please, if you have at least a couple of questions to ask Dr. Varun sir, we will take those questions. You can switch on the camera and just ask your questions, or you'd like to. Okay, sir. So we have a question from Mayuri. She says, how do we take false positives into account while using atmospheric modeling?
Okay, so false positive means again, this is something which you can't really quantitatively characterize, but yes, again, there are uncertainties in the models. And the only way to confirm that is through observation. So basically, they go hand in hand. So as I said, simple example I'll give you, like the general circulation model, the climate models. They are modeling the temperatures of the atmosphere. Now, I showed you the radiative processes. So I have a model which will give me the temperature structure of the atmosphere, say Venus atmosphere. And then I have this experiment called the radio science experiment, which gives me the actual observations, gives you the complete profile. So I compare those two profiles, and then I try to find out what is it that my model, where is it going wrong, or what it can. So that is correct. We have to validate these models more often, which we have done for the case of Earth. For Earth, we have millions of weather stations all over the world which are measuring everything under the sun. So we have ample amount of opportunities to model the Earth's atmosphere, but for other planets, it's difficult. All that we have is from the remote sensing missions or the very few land or so that is one of the constraints.
So the other question, sir, is do clouds actually play an important role in atmospheric modeling?
Yes, so that is something which I personally spend a lot of time. As I showed you one of the pictures, you have different clouds on these planets. On Earth, it is the water vapor clouds. But this water vapor clouds, they produce thunders and lightning there. Now the same thing is happening on Mars. On Mars, it is the dust particles which enter into the atmosphere. And we have shown through our modeling that these dust particles can get charged and even produce very large electric fields. And when these electric fields reach a certain breakdown potential, they can discharge lightning. Now, the issue is that this phenomenon has not been observed till now. So the question is, how do we model this lightning, which we normally understand as water vapor cloud generated on Earth? Now it is generated by dust on Mars. So that is what we have to do. The same macrophysical models that we have for Earth, we have done that for Mars, and we are trying to predict that whether we can have lightning. The same thing we are doing for Venus now, because we have a lightning experiment developed by PRL for the future mission. So if we can, model then, it is the sulfuric acid ions which can produce lightning.
Right.
Again, it's a very challenging question. Why do we not observe lightning where we have had so many missions to Venus? None. They are given some indication, and the scientists say that okay, this is indicates lightning, but no convincing. And we are always developing an instrument which is full time dedicated to observing the light. So this clouds is a very important sulfuric acid clouds, dust clouds, which we have to take into account into the model. And
Okay.
mm,
Okay.
no.
Yes. So, the next question is the lapse rate different for different atmospheric compositions?
Yes, that's what I told you that the lab rate is quite different because the composition, uh, it is indirectly affecting your temperature structure, and then the specific heat capacity is about that. It's again, so that's why I showed you it's quite
Right.
different.
Yes. Yes. So for different planets, it would be
It's
there'd be a
different.
very big difference.
Yeah.
Okay. So we'll just take a few more questions. The question is, can seasonal variations in atmospheric composition be considered as a biosignature?
Not exactly. Seasonal variation is coming because of the coupling of different photochemical processes with the solar radiation. Because that is what is changing. What is changing in the season, and that itself cannot indicate that biosignatures, as I said, in the atmosphere. All that we can say is that hydrogen, carbon, and nitrogen. If you're measuring that, that would be a better indicator.
Right. Okay. So then how do we remove the seasonal variations? I mean, if we wanted to.
No, we don't remove the mapping aspect. We really want to study that why, how are we varying seasonally? Why are they varying seasonally? At certain seasons, why do you have this, or why you don't have that? That is all related to the kind of processes which are happening.
Right. Okay.
We must apply to that.
Okay. And so how can we use the radiative transfer equation to understand conditions that may have led to the formation of organic molecules? Like if we look at icy bodies or other moons, uh, would this radiative transfer equation affect or lead to any of those kind of formations?
Yeah, so we can use that to study, even for example, comets, where things can, in very cold conditions, things can survive. So digital transfer can help you find out that what are the conditions where, such kind of temperatures exist, or low temperatures where the things can survive. This.
Okay, okay. All right. Mayuri, do you have a question? If you do, you can unmute. And
Yes, sir. I just wanted to ask you, can we use seasonal variations in atmospheric composition as a biosignature?
Yeah, that question, yeah, I just answered that. Seasonal variation itself you cannot is not an indicator because that just gives you how what kind of processes are responsible for giving that variation, and they might be different. Signature for bio will come only if you have those particular elements present there. So that is what, for example, curiosity rover is doing. They're trying to measure organics. Do you have organics there? Or do you have hydrogen, carbon, nitrogen, which represent life? How much it is there? So only if you measure the quantity of that, or methane, for example, how much methane is there? Those are indicators of life, bio markers. So first of all, you have to find them. Seasonal variability is the next step. You try to see why are they varying seasonally. What is the process which is leading to that? That will be the second aspect of it.
Thank you.
okay. Okay, so we'll just take the last question. What does the atmospheric model, I mean, what role do atmospheric models play in studying the atmospheric escape processes? And, how does it affect the long-term evolution of planetary atmospheres?
Yeah, that's a good question because planets, as you know, have evolved, and the escape is one of the important role played there. And I haven't gone into detail there. When you study an atmosphere, the evolution part is a very detailed process, as you pointed out, that there's a lot of escape happening. And one of the ways we are trying to study one of my PhD students is looking at the effect of space weather. You know, now that has become a buzzword. No?
Right.
Just like Earth's weather, you have space weather, which is affecting the upper part of the atmospheres, and how that can affect many of these species, which and then we try to determine the escape rates of many of the lighter species. What are the so those kind of predictions we are doing them. You cannot directly measure that. Escape is something which is happening all the time at certain levels. So all that we are doing is we are trying to estimate these rates, how fast and what is happening, how fast. And then there are models which can go back in time and sort of say that, okay, this is what happened. So escape is very important, and that comes in the upper regions of the atmosphere where the solar interaction happens. And that is again what we are trying to study. So different regions of the atmosphere demand different science.
Right.
Yes. Yes.
Okay, sir. I again like to thank you for taking out this much time to give us in your busy schedule in Germany. I hope the project is going well in Germany and things have settled down. With respect to the students, if they have any questions, you can please let me know. I will
Yes.
share the questions with Dr. Varun Sheel, and whenever is possible, he will definitely get back to us. So if they have any concerns or any questions, any follow-up questions, I'll definitely get in touch with you.
Sure,
And
sure.
I'd like to thank you from the Center of Excellence in Astrobiology. And so we can catch up a little bit later about the Ladakh expedition and so on a
Yeah,
separate
yeah.
call.
Sure, sure, sure.
Okay, sir?
Okay.
Okay. Okay. Thank you. Thank you.
Okay, thank you. Yeah, thank you.